Welcome to Module 1. We're going to cover how computers function. Module agenda, we're going to have 3 sections here in Mod 1, 1.1, 1.2, and 1.3. We're going to start out with numbers and how computers read numbers. We're going to take that concept further in Section 2 and start converting bits to see how numbers are read by computers, and then go into Section 3 where we're going to cover basic hardware and basic memory, introduction to computers. All right, let's dive in. Section 1, going over numbers. Now, there are important numbering systems to be aware of when talking about computers. As we've gone to school, we've learned about a basic notation here of base 10. This is your classic digits 0 through 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and there's actually a sub-representation of a base 10 that we don't even denote, but this is our basic decimal system that we've learned and grown up with in school. When we talk about computers, we're moving into binary numbering systems. So binary is built off of the base 2 instead of the base 10 numbering schema. When we talk about binary, we're only talking about bits. A bit is either a 0 or a 1. So is this a bit? No, that's a 3. That's a normal decimal number. A bit has to be a 0 or a 1. Is 0.0 a bit? No. Is this a bit? Yes. This is a bit. This is a bit. This is a bit. 6.5, not a bit. So a bit, just remember, it's only a 1 or a 0. And this is 1 bit, this is a 2nd bit, a 3rd bit, 4th bit, so on and so forth. And the base notation, without having to write it, is going to be base 2. The other important numbering system we're going to want to work with computers is hexadecimal. We're going to call this hex for short, and it uses the base 16 schema. And hex goes a bit further, and it's going to cover 0 through 9, but also A, B, C, D, E, and F. We're going to come back to this concept of A through F later on and what numeric values are assigned to them, but basically A is 10, B is 11, and then F would be 15. So instead of going to a decimal number of 10, hex notation is going to say, okay, that is A. The representation of hexadecimal is always going to have the 0x precedence. Then it's going to be followed by numeric or A through F letters. So we can have any combination here in hex. We can have 0, 1. We can have alpha, bravo. We can have 3, franc. All the way, any combinations from 0x00 being the numeric value of 0 to the highest value 0xFF going to be equal to 255. We'll see why that number is important later on, but just get a familiarity with the numbering systems associated with computers and which ones are kind of more important, being the binary and hex, and we're moving away from our decimal traditional academia learning. Now we need to cover the difference between a bit, a nibble, and a byte. Again, we're focusing on base 2 binary notation here. So a bit, as we've covered, that's a 1 or a 0. If we count up the number of bits we have here, we have 8 individual bits all in a row. This is how the computer is going to read any type of data you give it. All computers read data, whether that's your essay you're writing on your Word document, your PowerPoint presentation, this input from any device. It is translating all of these inputs in forms of data, audio, this microphone recording, into 1s and 0s. Just push the I believe button on that for now. We're going to cover that concept later on in depth, but just understand everything that the computer is doing it's in bits, ones and zeros, and it's just converting it in a way to be able to read it. Now, a nibble is going to be 4 bits. Any grouping of 4 bits, any combination of ones and zeros that are total length of 4, that's called a nibble. And then when you have 8 bits in length, that is going to be a byte. Now, I don't think anyone's really covering Nibble anymore, but definitely should know what a bit is and what a byte is. So a bit, again, a 1 or a 0, and a byte, any sequence of 8 bits in length. Now, where have you may have heard these terms before? Well, I'm sure you've heard of a gigabyte. If your internet service provider has sold you a gig internet service as your max bandwidth, I'm sorry, you're overpaying and you probably don't need a gig of internet bandwidth to work with. Just to give you an idea, a gig is very large. That's going to be 1 billion bytes. And this is not bits, it's bytes. So a gigabyte is 1 billion bytes. So if we multiply this by 8, it's going to be 8 billion individual bits, 8 billion ones and zeros all the way across to give you 1 gigabyte. Now, this is important to note as well. We're going off the decimal measuring system here for 1 billion bytes to a gig. Remember, that's our base 10 notation. But if we're talking about computers and their measuring system, we're going to be focusing on binary. So actually, 1 gigabyte is now a bit more than a billion bytes. It's 1,073,000,073 blah 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 bytes long. This can be confusing when you go to the store and you want to buy maybe a 16 gigabyte USB device for your external storage, and you don't know if they're selling you based off of the decimal measuring system that you grew up with to understand 16 as a whole number, or if they're selling you a binary measuring system, so you're actually going to get a few more bytes in there. Another place you may have heard these terms before, maybe you are an iPhone, Team iPhone. We are here at Blue Team Consulting, Team iPhone. And maybe you have the 256 gigabyte storage iPhone, or maybe you're in the 64 gigabit club. All of these terms we're going to be relayed and build on top of these as the course continues. But to give you a rough idea of what 1 gigabyte could be in terms of storage, that can be 250 songs. If all of you stored was just MP3 audio files, that's about 250 songs. It can be 6,000 emails. That's a lot of emails. And if you're, the iPhone user over here, just think about how much data, your pictures, your text messages, your emails, your contacts, all of that is taking up storage on your device. So if you open up the settings on your iPhone and you see how much storage you're using, well, you have 276 gigs. So that is 256 billion bytes of storage on your iPhone. We're going to revisit the concept of scaling from bits to kilobits to megabits to gigabits to terabit storage, and then beyond that is like petabytes, etc. But maybe you've heard of terabyte storage, or maybe you've seen files on your computer where your Word document that you're working on is a couple of kilobytes in storage capacity. You can see this in File Explorer on Windows or in Finder if you display your file size, or if you're downloading an application from the internet, how many gigs or megs of storage is it going to take up on your hard drive on your computer. This is where all of these concepts start to overlap. So just remember, a bit, a 1 or a 0, and a byte is any combination of 4 bits. Now, we're going to start converting binary numbers back towards our decimal notation. And we need to figure out how the computer is reading these numbers and convert them back into human readable format. So what we start off with is our base 2 exponential chart here. And we're going to go from 2 to the power of 0 all the way to 2 to the power of 7. And when we compute the math on this, 2 to the 7 is 128, 2 to the 6 is 64, all the way down to 2 to the power of 0 being 1. And we're going to leverage 128 to 1 to help us calculate a binary base 2 conversion to our decimal number, base 10, human readable number that we're familiar with. So how do we do this? Well, once we write out our 2 to the 7 to 2 to the 0 notation and convert that to a decimal number mathematically, all we do is write out where the bits are placed. So this binary number is 1, 1, 0, 0, 0, 0, 0, 1. In computers, a 1 means the bit is set and it's on. 0 in computers means the bit is not set and it is off. So I kind of like to think of, computers operate on electrical signals or literally just inputs. So if the bit is on, I like to think of the line going up, or if it's off, it's a 0. If we had another, so if we had like a 1, 0, 0, 1, 1, 0, it's on, so it sent an electrical signal, off, off, and then we had a 1 being written, another 1 being written, and then off. That's just kind of how my brain works, but just remember that 1 means on, so we're allocating the bit as set, and 0 means off. So now that we have our number here, we need to convert by adding up all of the numbers above. So since the bit is set here, I'm going to add up 128. The bit is set here, so I'm going to add up 64. All of these bits are off, and this last one is on at 1. So we have 8, 12, 13, carry the 1, 6, 7, 8, 9, 193. So this binary number of 11000001 becomes the decimal number equivalent of 193. Now we're going to do a lot of examples in this, and additional homework is available to you if you've purchased the books that go along with the course, but it will make more sense as we kind of get into the repetition here. So now we can do another example, and let's just select a random 8 strings of bits. So let's do 0, 1, 0, 0, 1, 1, 0, 0. Now, what does this binary number become? Well, we're going to add up 64, 8, and 4. 8 and 8 is 16, carry the 1, 76. So 0, 1, 0, 0, 1, 1, 0, 0 equals 76 in decimal. Remember to write out your 2's exponentially and then your 128 through 1 to be able to line up your bits accordingly. Now, as we continue on, I'm probably not going to write out this line anymore, and I'm only going to write out the 128 through 1 values because you're going to write this out so many times and you're not going to need your 2's exponents to be written every time. An easy way to do this is you notice the values just double. So 1 doubled is 2, 2 doubled is 4, 4 to 8, or you can go the other way and remember that it starts with 128 and then half of 128 is 64, half of 64 is 32. Whatever preference you'd like to do, just remember starts at 1, ends at 128. Now, try to convert this binary number to a decimal value on your own, and then when you're ready to work through the solution, go ahead and click unpause. All right, now we're going to convert. So we have first step, 128, 64, 32, 16, 8, 4, 2, 1. Our bits are 1, 1, 1, 0, 1, 1, 0, 1. We add up all of the bits that are set. So 128, 64, 32, 8, 4, 1. Geez. So 8 and 8 is 16, 2 is 18, 22, 26, 27, carry the 2, 6 and 4 is 10, 13, carry the 1, and we have 237. So that should be your answer. Move on to another example. Go ahead and pause if you'd like to work through this. Otherwise, we're going to move into the solution here. All right, first step, 128, 64, 32, 16, 8, 4, 2, 1. We set our bits. We have 1, 0, 0, 1, 1, 1, 0, 1. We add up our values, 128, 16, 8, 4, 1. 6 and 4 is 10, plus 16 is 26, plus 1 is 27. 5. We have 157, should be your answer. All right, one more example here. Go ahead and press pause, and then if you want to work through your solution, this is kind of a trick question, but we'll cover it here. Okay, first step, writing out 128, 64, 32, 16, 8, 4, 2, 1. Now, if you wrote it 0, 1, 1, 0, 1, that is incorrect. So what we're going to learn here is that computers read left to right. So we actually want to write this the other way, with it being 1, 0, 1, 1, 0. And since it's not 8 bits long, the rest of these are just assumed 0 off into infinity. So make sure you're doing left to right notation. And when we add up 8, 4, and 1, that is 13 should be your answer. So it's okay if you made the mistake of doing 0, 1, 1, 0, 1, 0, 0, 0. Now you learned computers read left to right, and always start with the lowest value first and then work your way to the left. All right, now that we have converted binary to decimal, we're actually going to go the other way. So how would we convert 255 back to binary ones and zeros? You can pause the video and try and figure it out now, or work through the solution with me. Okay, so how do we convert the 255? So what we do is we start with the number 255. Then we try and figure out what ones and zeros are going to be assigned and allocated. And we ask ourselves, starting on the left, does 128 fit into 255? It does, so we can allocate the bit, and then we're going to subtract 128. So 255 minus 128 is going to give us 127. Does 64 fit into 127? Yes, it does. Then we subtract 64. That's going to give us the value of 63. Does 32 fit into 63? Yes, it does. Subtract 32. It's going to give us 31. Start over here. 16 fits into 31. Minus 16. That is going to give us 15. 8 fits into 15. Subtract 8. That is 7. 4 fits into 7. That gives us 3. 2 fits into 3. 1 left over. 1 fits into 1. And then 1 minus 1 were fully allocated. So, a couple of things to note here. 255 is the maximum value that you can have assigned to 8 bits in a row. The lowest value would be 0. If all of these were unallocated, the number would be 0. So if you think about this as a chart here, you can always make any combination of zeros and ones, starting with 1, 0, 0, 0, all the way across to 1, 1 to make 3, or I guess a better one to do second was 2. So this would be 0, 1, this would be the value of 2, this would be the value of 3, this would be the value of 4, and you can do that all the way from 0 up to the maximum, if all the bits are turned on, 255. All right, try this one on your own, converting the decimal number 153 to binary. Okay, first things first, we write out 128, 64, 32, 16, 8, 4, 2, and 1. We're starting with 153. Does 128 fit into 153? Yes, it does. So we can allocate the bit. We do 153 minus 128. That is going to give us 25. Now, does 64 fit into 25? No, it does not. So we give this one a 0. Does 32 fit into 25? It does not, so we do not allocate that bit. Does 16 fit into 25? Yes, it does. So we can subtract 16, leaving us with 9 left over. Does 8 fit into 9? Yes, it does. Allocate the bit, subtract 8. We have 1 left over. Does 4 fit into 1? No, it does not. Does 2? No. Does 1? Yes. So we minus 1, and we are squared up. So 153 in decimal becomes 1, 0, 0, 1, 1, 0, 0, 1 in binary notation. Let's do 13. 128, 64, 32, 16, 8, 4, 2, 1. Starting with 13. 128 does not fit into it, nor does 64, or 32, or 16, but 8 does. Subtract 8. We're left with 5. 4 fits into 5. 1 left over. 2 does not fit into 1, but our 1 does. And we're squared up. So 13 becomes 0, 0, 0, 0, 1, 1, 0, 1. But it's repetitive to write out all these zeros because the zeros could go to infinity. So what we really just say is 13 is the binary number 1101. Now, as you've probably noticed, you're going to get very quick at doing these potentially in your head for smaller numbers. So if I asked you, what is decimal 10 in binary, you can probably just think of 8421 in your head, and you know that 8 and 2 need to be set to give you 10, and these would be zeros, and your 10 becomes 1010. That's kind of ironic that 10 repeats. But very simple. If you can work through it through your head, you don't need to write out 128 through 1. More power to you. But this is introduction to just converting numbers. Now, hexadecimal notation, we're going to take it a step further and be working with base 16. So in hexadecimal notation, each digit represents 4 bits of binary data, which makes it easier to represent binary data in a compact form for the computer. Instead of the computer having to read a bunch of ones and zeros in a row, it can compact it and read it in hexadecimal notation as well. So if we have the example here of converting the hex value of 15 to binary, take a second to pause and see if you can solution that. Otherwise, we'll work through the solution now. So we have our number system of 128 through 1, but when it comes to hexadecimal, we're going to have a different approach. We're going to break up the 1 and the 5. And then the 1 is going to get its own set of 8, 4, 2, and 1, and the 5 will get its own set of 8, 4, 2, and 1. If you remember, this is 1 byte, which means this is 8 bits. So we can allocate 4 bits over here to the 1 and 4 bits to the 5 over here. Now, in order to get the value of 1, we allocate the 1 here, and the rest would be zeros. To get the 5, we do the 4 and 1 to get these values. And now we have our 8-bit length zeros and ones to then map to our 128 2 to the power 7th chart. So we would have, taking from the bottom here, 0, 0, 0, 1, 0, 1, 0, 1. 16 and 4 is 20, plus 1 equals 21. Shout out Vine. So this may seem confusing at first. When we go into networking and protocol analysis and leveraging Wireshark, we're going to see this a lot easier, and converting stuff will become like second nature. So hexadecimal, if you don't pick this up right away, don't worry about it. I definitely encourage you to go out and research some other tutorials about how to convert hexadecimal to binary and then binary to decimal, just so that you're familiar with it. But again, we're going to revisit this concept later on. And if you purchase the books for the course, you have additional homework, practice, and solutions in there as well. Do one more. So we have hexadecimal Bravo 6 to convert. So first thing we do is break out our Bravo into 8, 4, 2, and 1. And then we have our 6. Going to break that out to 8, 4, 2, and 1. The only combination of 6 that we can have is 4 and 2. These will stay zeros. Now, Bravo, as we mentioned a long time ago, and I'm sure we've forgotten, we have the values 0 through 9 already set. We just write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But hexadecimal, remember, adds the values of A through F. So after 9, it's not going to write it as 1, 0. It's just not how computers work. So alpha becomes the value of 10, B becomes 11, C is 12, D is 13, E is 14, and F becomes 15. Now we have a way to write out 10 through 15 using alpha through Frank. So Bravo has the value assigned of 11. So how do we make 11 out of this? Well, 8 goes into 11. And then we would have 3 left over. So we know we need to set 2 and 1. We're just working that out on the side. We had 11, subtracted 8, 3 left, subtracted 2, 1 left, squared up at 0. So we had 1, 0, 1, 1, because Bravo was given the value of 11. Now 6, pretty easy, we already converted that. And now we just do our calculations of 128, 64, 32, 16, 8, 4, 2, and 1 for our 8 bits here. And we have 128 allocated, 32, 16, 4, and 2. And if we add all of these up, 128, 32, 16, 6, 182 if I put that into my calculator correctly. So 0xb6 is the binary number of 10110110 and the decimal number of 182. For a challenge, if you can take 182 and convert it back to a binary, that would be good. And super bonus if you can convert the binary back to hexadecimal, or even decimal back to hexadecimal. We're not going to cover a bunch of examples here, but if you go out and try and make sure you can convert binary to hex to decimal and any of those combinations, you're going to be in really good shape.